Hello, students. Today we want to talk about implicit differentiation. This is a technique that we will find to be very useful in calculus and also in the sciences and engineering. When you continue in your work to Calculus 3, implicit functions will have an even larger role in your study. And the idea is that we invoke what we call the implicit function theorem, which allows us to differentiate implicit equations in several variables. And so what we're going to do today is to discuss the difference between the explicit and the implicit equation and use a technique which you actually already know how to do. I'm just going to make this idea available to you. So let me share the screen. I want to start out with a very simple example that will help you understand that this technique is readily available to you. For instance, I've written an explicit equation here as you've been doing your work with differentiation theorems. All of the functions, of course, are written explicitly, and usually you have functions of several different variables, but maybe functions of t, functions of x tend to be the most popular ones. And of course, as you work with any type of discipline, you can use whatever letter you like for the independent function or independent variable. And of course, we understand in engineering and physics that formulas can take on very different forms, and usually the variables we use have some indication as to what that variable represents. So here we have an explicit equation, which you're accustomed to, y equals x times sine x. That is, we have explicitly solved for y in terms of x. And that's what we're accustomed to. Now, the implicit equation, which again allows us to think about implicit functions and the implicit function theorem, which again relates to differentiation with respect to several variables. And again, what we want to do is take a very simple example here, which I have noted is the unit circle. When we think of the unit circle, we think of standard trigonometry and how we define sine and cosine. So we look here and notice that we have not solved explicitly for y or explicitly for x in terms of y. So we call this an implicit equation. Now, to give you some idea of what I was talking about with implicit functions, a very common technique is to transpose all variables to one side of the equation and then construct a function of two variables and call it uppercase F of x and y. So we have big F equals x squared plus y squared minus 1, which is 0. So we have an implicit function. So what we can do, and again, this is just a notation that you will use later. I'm simply trying to give you some idea as to why we use the terminology that we do. But the main thing that we have here is we want to treat y, if that's our choice, treat y as a differentiable function of x and differentiate functions of y using the chain rule when we have compositions. And the idea is that why do we have compositions in this case? Well, if we were assuming that y is the dependent variable, then it is necessarily a function of the independent variable x. And so we can't assume that we actually need an explicit copy of y. That may not be possible. For instance, we may have several occurrences of y in an equation of different powers where the explicit solution is impossible. But with this implicit technique, we can always compute the derivative, at least where it would be defined, in terms of all of the variables, in this case, X and Y. Now, one common use, for instance, if we think of N as a rational number, and we want to differentiate a power of Y as a differentiable function of X, well, we use the power rule in conjunction with the chain rule. So we have N, Y to the N minus 1, and I'll put a little dot here for multiplication, times Y prime. So Y prime is the symbol for the derivative of Y, in this case, with respect to X. And so there are other notations, as you have noticed in your textbook, using the Leibniz notation, dy dx, which mimics the delta y over the delta x that you see often in physics texts. So what we're using here is a very useful notation that's not ambiguous, but it's easy to write. And so we could think of differentiating implicitly, that is, differentiate each variable with respect to its dependence or independence, and then solve for Y prime. And let me show you a very simple technique here. Now, of course, if I use the notation that I have here, we would say that we just want the X derivative of F. And of course, there will be more about this notation when you get to Cal 3. But for now, we're just taking the X derivative of F as a subscript here, X being the subscript of the capital F. And so we just take the derivative as we move through using our little rule here. So we have 2x, and then of course we have 2y, y prime, and the derivative here, of course, of -1 is 0, so we just don't write another 0, and of course the derivative of 0 being 0. So basically, I'm still kind of thinking of this as an equation, which you certainly can do. And so that gives us the ability to actually isolate the y prime. So now we have an equation in x, y, and y prime. So we can simply, at this point, well, the first thing, we're going to retire the 2's because they're just in the way. Just divide out the 2's and multiply by 1/2. And then at this point, we can just retire, in this case, the x to the opposite side and divide by y, of course, assuming no division by 0. So now, basically, we have algebraically solved for y prime, and we get the expression, the additive inverse of x divided by y. Okay, so again, doesn't look like what we're accustomed to, where we just have one variable. But again, we are treating y as a differentiable function of x and using the chain rule to differentiate it. Now, that doesn't mean you don't use the other rules. Of course, you could use the product rule, the quotient rule, the sum rule, all of these rules in conjunction with the chain rule. So all of those techniques are still valid. So you're thinking if you treat equations that you've looked at previously, the implicit technique does not change anything. It just simply is an alternative. So what we can see here is we don't necessarily have to solve for y as an explicit function of x to determine a formula for its derivative. Even though this is a simple case, if we solve for y in terms of x, we would have radicals. And this avoids that. So we get a very simple expression for the derivative. And sometimes we just call this the Cartesian derivative, the derivative of y with respect to x. And now one thing you can notice here, if we remember the original equation, this expression would be 0. That is, x would have to be 0 for a horizontal tangent. Of course, y being non-zero or plus or minus 1 using the original equation. And then the vertical tangents that we know we have would exist upon y being 0. That is where we have an unbounded derivative. And then, of course, the values of x would be plus or minus 1 using the original equation. So there is benefit, and we will also see this benefit in Calculus 2 when you talk about parametric equations where you define curves in terms of parametric equations, and then we will show you how you can actually retrieve the standard Cartesian derivative from the derivatives of the parametric equations. And of course, that's going to be another topic that you'll see later, and we'll find it very useful when you start talking about the geometry of curves. That's something we do at the end of Cal 2, and then of course there's a large section on that in Calculus 3. There's also differential geometry of surfaces, which some of you will take as you continue your education. So the idea here is that if you don't even want to think of writing an implicit function, you can simply take the original equation here and just differentiate it with the standard techniques. So differentiating the sum would just be taking the derivative of each term here and adding it, the sum rule, and then of course applying the chain rule here to the differentiable function of or the y as a differentiable function of x, again applying the power rule, and then back to here. So how you want to think about it probably initially is easily done by just simply taking the equation and differentiating it, with the assumption, again, that y is a differentiable function of the independent variable x. Let me also emphasize, as I have already said, it does not matter which variable you choose to be dependent or independent. It may just be a function of the type of problem you're working on. When you work with differential equations, you may find it more convenient to assume that x is a differentiable function of y and proceed that way. You have the complete flexibility with implicit functions to work with them as you need for the problem that you are actually trying to solve. So even though we're focusing on y as dependent, that certainly does not have to be the case. We will find when we talk about related rates is that we will assume every variable is a function of t, where t will be now independent. And so when we use the chain rule, the primes will just be t derivatives. So the implicit technique is extremely useful and extremely valuable. And again, you're noticing here that we didn't really have to learn anything new. All of the theory is already present. It's just how we are choosing to apply it. Okay, now what I want to do is a fairly interesting example. We want to, of course, you can see that the algebraic part of implicit differentiation will not be that difficult. Certainly more terms means more algebra, but I wanted to say something about an inverse trigonometric function. We will have the opportunity to use the inverse function theorem, which is the precursor of the implicit function theorem, but I want to use this implicit technique to actually find the derivative of the inverse secant. So let's just remember, back in pre-calculus, we would say that y equals the inverse secant of x if and only if x equals secant of y. Those would be the inverse equations in the sense of how we actually define the inverse sign. And then, of course, as we compose them, they just undo each other because they're inverses to give us the identity function. Now, when we think about the construction of these functions using the geometry of the unit circle, we need restrictions to make them one-to-one. So the first restriction here, we have x in absolute value is greater than or equal to 1. And of course, y would live in the interval 0 to pi over 2, excluding the pi over 2, because that would be a vertical asymptote of the secant function. and then pi over 2 to pi. And this is a standard definition of for our calculus text for inverse sine. Other texts will change this portion. And again, every time I apprise students of this function, I'll just say, be sure that you check what the particular textbook is using. But the consistency is still there. It's just that there at this point does not seem to be a universal definition of the inverse secant, which is really seems to be unnecessary. Of course, the inverse sine, the inverse tangent, the inverse cosine all have universal definitions. So when we look at this, we look at the original equation, and then we look at the equivalent equation, which again is a nice implicit equation, or explicit if we like. That is, x is solved explicitly as a function of y. And so we can now treat this with the implicit technique or just the standard differentiation technique, however you want to do it. But what we are assuming here is that y is a differentiable function of x. And so that is the premise that we have to set up if we want to find y prime. So let me just write down here. I'll just say use the implicit technique to compute y prime. But y prime in this case would just be the derivative of the inverse secant function. So we would say inverse secant of x prime. Because what we have in this particular case is all of the ingredients to differentiate this, because we understand the derivative of secant. That's something we've learned in our previous lectures. So when we think about this, we're happy to look at this equation in a different manner. So now we'll just focus on this equation and differentiate. So I'll go ahead and write it as differentiating an equation. So we'll have x prime equals secant of y prime. And of course, I'll note y is a differentiable function of x. So that is the assumption that you always have to make when you're differentiating implicitly. What is the independent variable? What is the dependent variable? Or it could be a whole slew of variables. For instance, you might have a function of x, y, and z, and z depends on x and y. So the x and the y would be independent. So again, the flexibility of this technique is far-reaching, and it is a cornerstone of what we do in calculus and analysis. So, of course, differentiating with respect to x, the derivative of x relative to itself is just 1. And of course, the derivative of secant y is secant y tangent y times y prime. And I'll put the little dot there so we make a notion, a little bit more of the emphasis on the y prime. And let me make the t a little bit better here. So what we see now is that we have the variable y prime for which we can solve. And again, assuming that we are not dividing by 0. So equivalently, y prime will now just be 1 divided by secant y tangent y. Now, of course, at this point, the secant y is not 0, but this would exclude the 0 and the pi, because as we divide, the sign, of course, would be 0 there. So now we're looking basically at y living here. So we've cut down things a little bit. Just thrown out two endpoints. There's no difference here. This is like doing a trigonometry exercise. We're pulling in all the ideas that we already know. Now, of course, we have a formula for the in this case, the derivative of y, but it's relative to the variable y. And since we start with y is the inverse secant of x, we want to rewrite this in a manner that will allow us to make that transition. So first, we're going to use the Pythagorean identity on tangent and focus on each of these. So I'll put a box around this and call this 1, and then a box around this interval and call this 2. So let's look at 1 first. Now, what we notice, and we won't have to do this twice, is that we can use a Pythagorean identity on tangent. So I'll just say, recall secant squared y equals 1 plus tangent squared y. So, of course, we can solve for tangent squared just by subtracting the 1. Again, just something we do in trigonometry. This is a fundamental identity rewritten, and we find them to be very useful, as we've already seen in our work. So now we can take plus and minus square roots of this as we need. So for number 1, as we notice here, the tangent has the positive sign in this interval. So this would imply that y prime equals 1 divided by secant y, and then I'll just use parentheses here, secant squared y minus 1 to the 1/2 power. And now we're ready to move to the x variable, because we know what y is. It's the inverse secant of x. So again, because we're dealing with this particular interval where the tangent is y, we have established the sign of the tangent with the correct sign for the square root. So now we get 1. So we have secant of the inverse secant of x. And then we have secant of the inverse secant of x all squared minus 1. Using the 1/2 power just because it's a little bit easier to write than the square root symbol when we're doing derivations. So now, of course, this is where we call these the inverse equations. Remember, when you compose the function with an inverse, then that reduces to the identity function. So, of course, we get x here. And then, of course, we get x, but it's squared, quantity squared. So we have, well, let me write the x instead of a 1. So we have x. And then I can use the square root symbol now, and x squared minus 1. So that gives us an algebraic form for the derivative of a transcendental function. So what we're seeing here is, with this technique, like I said before, we're working with transcendental functions, and then as we apply the implicit technique, we see that the derivative has the algebraic form. So let me just write this here, y prime, at least for this particular interval, gives us this. Now we need to see what we get here and see if we can combine the two cases, but we don't have to repeat all of this. Now for 2, we're just going to take the tangent here, but notice when y is contained in pi over 2 to pi, this implies that we must choose the additive inverse of the radical. That is, we need the negative sign, so to speak. So tangent of y will be replaced with the additive inverse of secant squared y minus 1 to the 1/2. So we have to choose that particular sign of the radical. And now we don't have to repeat all of this. This will imply now that instead of just, as we notice here, we get the additive inverse of x in both cases. Here it will absorb, but here it doesn't. So we'll go ahead and skip to this part where we take this and run it to here. So we have y prime equals 1 over the additive inverse of x. And then, if you will, well, let me write this correctly. Let me start out by just putting in everything with not skipping a step. So let me put the x here. And now I'll say times, and then I've got the negative radical here. So I'll put the negative like this, so it's in parentheses, then the radical, x squared minus 1. So that's a little bit more clear. So note the only difference here is that when we move to this point, we have the negative. So I'll just add an additional step. This just implies y prime equals 1. And then, of course, we have the secant y here. And then I'll just use parentheses. And then we have the negative of this radical. Now I'll use the radical since I don't want to use too many parentheses. So here we go in all these different forms. So when we compare the two, the difference is the sign of the tangent, which now here is negative. And so as we move from here to here, which again, we don't have to repeat, we're just replacing y with its definition here. And so instead of just this, we actually get these same expressions, but with the additive inverse from here. And so now, and this was what I was going to write initially, but I felt like that was skipping too many steps. We kind of need this step so you can see how it compares to the first. So we have the additive inverse of x. And then here, we'll just go ahead and write this as x squared minus 1. Now notice, and we've got to go back to the original definition. When y lives here, x, again, we throw out the 0, x is greater than 1. Okay? And now, of course, when y lives here, the x is less than negative 1. So the branches of the inverse secant function correspond to the positive and negative values of x. So x is less than negative 1. So there's a little bit more arithmetic here, and at least the implicit technique allows us to see that. But this, again, is more of a trigonometric exercise. And so now you're thinking, well, if x is negative, then the additive inverse of x is its absolute value. So what we can do is simply write 1 absolute value of x square root x squared minus 1. Now, of course, here we could do the same. Since x is positive, we could simply replace it with its absolute value without losing any information. So when we look at both of these, we now have the way to combine them. That is, I mean, this would be, you know, a little bit overkill since x is always positive, but the key is that when x is negative, we have the negative sign here to affix to the variable x, which now defines it as its absolute value. So that's how we combine the two cases. We don't get a function in pieces because we don't have to. We can use absolute value. So now we have a summary. So what you're seeing is that by looking at this in terms of implicit technique, we have a very, very convenient way of determining the derivative. So now this implies, again, as I've combined the cases, secant inverse of x derivative is now just 1 divided by the absolute value of x times the square root of x squared minus 1. Now, of course, later we'll talk about inverse hyperbolic functions at the end of the course. And in Calculus 2, you usually start talking about the inverse trig calculus. It just depends. Usually that's held off until Cal 2. And so we normally teach the hyperbolic and inverse hyperbolic in Cal 1. Otherwise, they just get left out completely. But again, the techniques are the same. It's just that the hyperbolic functions have a rich calculus based on the natural log and exponential, which you learn at the end of Cal 1. So that makes a more natural transition to study that. So now we have, via the implicit technique, a derivative for the inverse secant. And then, of course, now we can let u be a differentiable function of x. So suppose u is a differentiable function of x. And then, of course, the assumption is that here that, of course, u in absolute value would be greater than 1. We kind of kicked out the equal to 1 because of the division by 0. But again, that's tacitly assumed. You don't necessarily have to write that, but you can look at the form and see that that would be the case. So by the chain rule, we would say that the inverse secant of u derivative relative to say an independent variable x, if you will, or whatever variable you chose, would now be, again, we multiply by the derivative of the inner function, which is u prime. So we would have times of u prime, which we can just put in the numerator, absolute value of u, square root of u squared minus 1. So this gives us a chain rule. We're going to call this the chain rule extension. And normally we just say times u prime, but we just go ahead and stick it in the numerator just for convenience. So the derivative of the outer function times the derivative of the inner function. So if you're taking the derivative of the inverse secant and you have an argument other than just the independent variable, you can just use the chain rule to extend this. So the chain rule extension is something we found to be very useful in our last section, because we couldn't get very far with differentiation if we had no way to understand the derivative of a composition, because so many functions are compositions and we can't just ignore it. I mean, you take the derivative of the square root of x and the derivative of the square root of x squared plus 1, very different. They're different functions. The inner function in the first one is x. The inner function in the second is x squared plus 1. And so you would not anticipate that the derivatives would be the same. Of course, they're not. So the key here is that we will continue to use all of the theory that we've already amassed and add to it. And so, of course, the study of calculus is very sequential. Now, of course, as we learn integration techniques, we will continue these derivative formulas and work them backwards to get nice antiderivative formulas, which will basically be the elements of an integral table. So that will come eventually. But I thought this was an interesting way to utilize the implicit technique to get a differentiation formula. Now, let's just look at a simple exercise where we need to actually compute, if you will, an equation of a tangent line from an implicit curve. Again, if you look in the notes, the lecture notes, you'll see that there will be some use of polar coordinates to get you to think about those. And I make a comment where in some cases, the polar coordinates can be very simple. In other cases, they may be difficult, just depending on the nature of the curves. But I often put that in there to get you thinking about topics that will come at the end of Cal 2 when we actually discuss polar coordinates and the calculus that ensues from the polar coordinates and the parametric equations. So in this case, example, compute a tangent line at the, well, tangent line to the curve at the given point. Now, just remember, it doesn't matter how you work with an equation. You can transform it algebraically and still get a correct form of the derivative. It may not look the same, but it will still be equivalent. So here's the particular equation that we have. We have 3, and of course it looks very polar because of the x squares and the y squares. Quantity squared equals 100 times x squared minus y squared. And the point in question that satisfies the curve is -4, -2. So as you saw in the notes, I made substitutions here, which were natural based upon the use of polar coordinates. You know, when you think of Cartesian equation that you think you could simplify using polar coordinates, you do it. There are many curves that have simpler representations in polar coordinates that you're going to find out about in Calculus 2. And you may see some of it in physics classes before you get to it. But coordinate systems can definitely simplify the mechanics of a problem. And if they are convenient, we will certainly make use of them. Now, what we want to do is just use the implicit technique. So I'll just write this, use implicit technique. Now, and again, just for convenience, we need the equation of a tangent line to the curve. So again, we will assume y is a differentiable function of x. So when you set out, you have to decide what's the independent variable, what are the independent variables? There's only one here, and what's the dependent? And so then you can move forward with this. Now, notice, if you will, that as we differentiate, we can apply all of the rules that we know. And then we want to isolate y prime and then evaluate it at this point. And then we can just use point slope to write an equation of a tangent line. So just like you did before, where you need to evaluate the derivative at the given point, and since we don't really care to solve for y explicitly, you know, we've got a fourth power here, and then you're going to have a mixed term and all, and that really would not be something we would want to do, or that we could even do easily. And if we can't do it, it doesn't matter that that is the case. The implicit technique will still allow us to write a formula for the derivative in terms of x and y, and then we can simply evaluate the function that we derive at the given point. So let's do that. So now what we want to do is just differentiate. So I'll write that process down so it's clear what we're doing. So again, prime everything. So now when we prime, of course, the three we can just factor. It just kind of stands out to the side. And then, of course, we had the chain rule times 2 x squared plus y squared. And I'll just write, I won't write to the first power because I don't want you to think it's a prime, but of course, that'll be the first power. And then, of course, times the derivative of the inner function, which will be 2x plus 2y, y prime. Remember, y is the differentiable function of x, so by the chain rule, we get the y prime. Of course, if you're solving for y prime and you forgot the y prime when you differentiated, you have to go back and put it in because you can't solve for something that's not there. This will take some practice. You will forget the primes. And again, you have to remember the assumption here. We don't have an explicit equation, so we must assume that y is a differentiable function of x and treat its derivative via the chain rule. And so now, of course, here we've got the 100, which is just a constant, and then we have 2x minus 2y, y prime. Now, what we want to try to do, again, is solve for the y prime, but we want to get rid of any extra stuff that we see here. Notice the 100 is just 50 times a 2. And we look for all the 2's that we have. We got 2's here and we got a 2 here, so we can absorb all of those. No need to just let them hang out. So this 2, again, this 2 multiplies everything, so they absorb. And then the 2's here can absorb the 2's here that if we factor, we'll have another 2 hanging out. So we'll go ahead and absorb all of this. So no need to hang out with all the extra numbers. They just get in the way. So look, we've got what, 3 x squared plus y squared. And then we have x plus y, y prime equals, and of course the 50 survives here. We have 50 times x, or the quantity x minus y, y prime. So now what we want to do is get the y primes together. So let's go ahead and multiply things out to do that. Notice here, and this will be the easiest way to do this, we have the y prime times all of this. So let's do that first. So equivalently, I'll just write the y prime first, y prime, and then just stick the y in with the 3 times 3y x squared plus y squared. So we multiply y prime times this factor here to give us this. And then, of course, we have the x times the same factor, which we can just vary or just leave out to the side. So plus 3x x squared plus y squared. Again, the algebra is how you want to make it, but we need to isolate the y primes. So again, multiply in a way so that you kind of highlight the y prime and then don't forget any of the factors. Just neatly write them out. And then over here, we've got, this is a little easier. We have a 50x and we have, if you will, minus, we'll just do the y prime out front times the 50y. Again, the order doesn't matter, but I want to make sure that you can see the y prime. That's a 50 times the negative y prime. So we just stick the y prime out front. Now, what I want to do is kind of highlight the y primes. Now, this may be fairly pedestrian and maybe more than you need, but if you get used to this technique and being a little bit more succinct about how you collect terms, you'll get the problem right the first time. So now we just want to put everything on one side, get all the y primes together. So now we have y prime, we'll just use a bracket. So we have 3y times x squared plus y squared. And then when we transpose, this just becomes a plus 50y, plus 50y, like that, okay? And now we want to, again, let this term join the 50x. So we have 50x minus 3x times x squared plus y squared. So I think most calculus students are happy with the implicit technique because you don't have to learn any new calculus. It's just an algebraic maneuver. And not overly difficult, but a little bit different from what you've been doing. But this helps prepare us for the mechanics of optimization problems and working with derivatives with the new theorems that we'll get in the next chapter. So we always want to make sure everything's nice and neat. So now notice we can just symbolically divide by the coefficient of y prime to get a formula. And of course, notice here we've got a y and everything, so we can factor the y. So y prime will equal, and of course here we've got an x, so we can factor that if you want, not required. So we have x 50 minus 3 times x squared plus y squared. Doesn't really matter what these look like, just work them in a way that you can easily substitute. And then the y's we can factor. We have y, we've got 3 times x squared plus y squared plus a 50. So this gives us a formula for y prime. Again, remember, whatever theorem you need to use, if you've got products, you have to use the product rule. If you've got powers, you're always going to be using the chain rule, but whatever differentiation rule you need, you will have access to it. Okay, and so don't make it up. Just if you've got a product, use the product rule. If you've got a quotient, use the quotient rule. I mean, all of the machinery that we have theoretically for differentiation is available to us. So now we've done the hard part. So all we need to do is make the evaluation. So this implies we think of the slope when we think of slope as m, and this will just be y prime -4, -2. So we just want to substitute these values into here. So I'll write these here. So this is going to give us a -4. And then we have 50 minus 3. And of course, if we square the -4, we get a 16. We square the -2, we get a 4. And then downstairs, we have a -2 for y. And then we have 3, and again, x squared plus y squared. Again, don't worry about writing out every step. If the numbers are easy to square, go ahead and square them. So we have 16 plus 4, and then plus a 50. So now, of course, the -2 absorbs into the -4 to give us a 2. And we have 50. We have minus. Now, of course, here, you're thinking you could go ahead and factor some things. So let's go ahead and say this is a -3 times the 20, and then we can factor that to make it a little bit smaller. And then downstairs, of course, the -2 is gone. We have a 3 times the 20 plus a 50. So at this point, if you want, you can go ahead and factor a 10 out of all of these. So you got 2 times a 10. So that's a 5 minus a 6. So again, this is a 60 now. 3 times the 20, factor the 10, that leaves behind the -6. Factor the 2 in here, excuse me. Of course, that leaves behind the 5. And then downstairs, we do the same thing. If you like, we have a 10 that we can factor from each one, so 10. And so, of course, that would be a 3 times a 2, which is a 6, plus a 5. This makes the numbers a little easier to break them down, but you choose whatever technique you like. Now, of course, the 10s absorb. And so we have 2 times a negative 1, so that's a negative 2, and then an 11. So that gives us the slope of the tangent line to the curve at this point, and now we just put the point in and we're good. So point slope, we have, okay, let me just put the point over here, P, -4, -2. So this will be Y plus a 2 equals -2 over 11 times X, of course, minus minus again, plus a 4. So equivalently, we have Y equals -2 over 11X. And of course, when we multiply here before I worry about that, we've got what, -8 over 11. And then, of course, we have the -2, which we can write as, so just multiply that. So that would be what, a 22 over 11. So multiply above and downstairs by 11, and then transpose it gives us -22 over 11. So this would be Y equals, and of course in the slope-intercept form, -2 over 11. I guess we'll just go ahead and stick the X up there in the numerator. And then 22 plus 8 is 30, so -30 over 11. So that would give us an equation of the tangent line. Now, again, the technique is what it needs to be. That is, you treat the equation implicitly with respect to differentiation, assuming this premise from the start. So that kind of guides us through it. So every time we differentiate functions of Y, we necessarily get a Y prime, applying all of the same rules that we normally do. So once we have differentiated the equation, it's kind of like we've applied theory in previous problems, and then we want to neaten up the process so we can analyze maybe what we have, or write it in a form that provides information that is important to us. And so here, once we have differentiated, we just algebraically solve for Y prime and then get a function in terms of X and Y. And again, a lot of times if you try to factor the function or write it in a way so that the powers are maybe more spread out, it's a little bit easier to evaluate, and maybe that takes a little less time. And then, of course, with the tangent line, the form is usually dictated by the problem, the point slope, where we use the slope of the tangent given by the derivative in the given point to get our equation of a tangent line. So again, we always say an equation of the tangent line because of course it's not unique. But when we write it in this form, it kind of forces it to be, unless we just want to multiply by pi divided by pi. You have so much flexibility with equations and things. And so the nice thing about the computer algebra system, whatever you type in, as long as it's equivalent to a correct response, you get a check. Now, again, I hope it's starting to be clear as to how valuable this technique can be. The implicit technique is very useful, and you can see and probably already think about some ideas that you can use when you work on science and engineering problems. Now, another type of problem would be, for instance, we know we can calculate first derivatives, and we can go an additional order of derivative and calculate a second derivative. And so I want to show you a technique with that. So in this case, we want to start with the first derivative. So we have an equation. So I'll write this compute Y prime and Y double prime. So you're thinking, if you compute Y prime, you get a formula in the variables X and Y. And so Y double prime will just be that equation differentiated again. but of course you'll generate more y primes. And so the goal is an equation that doesn't have primes. So if you have a formula for y prime, you can substitute into the computation of the y double prime and then get the equation or the formula in x and y. So that would be the only additional piece of work that you would have to do. But the additional algebra is probably the part that makes it a little bit longer, but certainly makes it available to us. Now here's an equation. Here's an implicit equation, and we'll say we've got x squared, y squared, minus 10x equals 7. Now, with the last problem, we certainly didn't feel like we had to make any changes to it. There was no problem with doing the technique we did, and had we tried to make it simpler, I don't think that would have mattered much. But I will make a comment here. You can rearrange the equation to suit your purposes. In the lecture notes, I've done a problem that's very similar to this, if not the same one, where I leave it alone. That is, you just work it as is. And that's fine. Now notice, if we work it as this, and you could look in the notes, we'd have to apply the product rule here because we have x squared times y squared. And then, of course, 10x would be an easy derivative, just a negative 10, and then, of course, a 0. So the idea is that doesn't look, too difficult. We're thinking, well, that would be a way to solve for y prime and easy enough. Now, I want you to be aware that when you actually work on something like that and you try to figure out a particular formula, you might be thinking, is it easier if I rearrange the equation and make the process simpler and maybe only generate fewer y primes, so to speak? Now, I have an example I want to show you. I just want to show you the difference here between the notes and another technique that I'm going to use. Okay, so, and this will be good. Notice here's the same equation. And what I've chosen to do is to just differentiate it as it is. And we get this. Okay, now, what I want to show you is we can actually do this another way. This is certainly equivalent, and you end up with lots of algebra to get y prime, and it's doable. That's one way. Now I thought just to look at this from a different standpoint, maybe to make the process a little bit simpler, is I want to write an equivalent expression of this that you may find to be a little bit easier. But again, it just depends on how you want to look at it, because I want you to feel free to rearrange the equation and then differentiate, because you have that ability. Now, the actual formulas can be shown to be equivalent, but when you actually produce the formula, it will look different. And so this is what I want to share with you, that it doesn't make the problem wrong if you're working the problem with a colleague and you rearrange equations and your derivative formulas look very different. Well, you can work them backwards and show that they are equivalent, but in lots of cases, you don't really want to do that. So just remember, when you do a computation and you rearrange the equation, the computer algebra system will scan your formula. And if it is equivalent to a correct response, then it, of course, is correct. And so that's the beauty of the computer algebra system that can scan your work and allow you the flexibility to try different techniques. And that, I guess, one of the major pluses about technology is that we can hypothesize and try new techniques and then make sure without, undue effort to show that we have indeed an equivalent response. Now, of course, many times I just do that by pencil and paper and make the verification myself. But I don't want you to think that if you don't apply the technique directly to this equation, that you won't get the right answer or won't get a correct answer. So that I want you to put away and start with any kind of equation that you think will work for you. So now let's just do that. Let's just do a rearrangement just for fun. So this will give us a 10x plus a 7. And now, of course, you're thinking this is going to turn out to be a little bit more explicit. So I'm going to solve for y squared, of course, assuming x is non-zero. Now, what you see here is very simple in the sense that you have y squared is equal to a function of x. So that in and of itself is simpler. And this would be equivalent to the original equation. What's an identity? An equation that is valid or true for all values of the variables for which it is defined. So we have an equivalent expression of the original equation. I think sometimes it's just good to push the envelope just a little bit, just to make sure that okay, if this technique works algebraically, then I should be able to rearrange the equation. And again, I just want you to feel free to do that. You might be doing a physics problem, and it's more convenient to work with another form of the equation and move the problem forward more quickly. So now when we differentiate, we'll apply the implicit technique. So let's say apply implicit technique. So now we'll apply the derivative. Now that we've become professional, we have what? 2y, y prime. So apply the chain rule, power rule with the y prime derivative of the inner function. Again, and let me make that assumption. Y is a differentiable function of x. Is a differentiable function of x. So that's the premise behind what we're doing. So now we can just apply the chain rule, the quotient rule, just to get practice with that. So we'll have the derivative of the numerator, which is 10 times x squared, minus the numerator, which is 10x plus 7, times the derivative of the denominator, which is 2x, divided by the denominator squared, which is x to the 4th. So that was easy. Again, remember here we had to apply the quotient rule. Again, you know that well. You use it, very, very handy. So now when we look at this, let's clean this up a little bit. So if and only if, before we divide, we have 2y, y prime equals. And so now we've got, in this case, we'll collect some of this stuff. We have 10x squared. And if you note here, we'll be able to factor a 2 out of this. So let's go ahead and do that, because the 2 will absorb from the other side. So let's just go ahead and write this as 2 times 5x squared. And then we'll just run this up front, if you like. So we'll have plus 2. And then we'll multiply through here. That'll give us what? A negative 10x squared. So the x and the 10 with the negative and the other x. So 10x squared. And then, of course, the 2x, so that's minus, well, actually just the x, so that's minus the 7x. So notice I brought the 2 up here, got the plus, and then x times the negative 10x is a negative 10x squared, and x times the negative 7 is negative 7x, divided by x to the 4th. So that just creates some more convenient algebra. And then, of course, all these 2's absorb. So we have equivalently, just waiting out the divide until we clean up the right-hand side, y prime. So we have 5x squared, and then we have minus 10x squared, and we have minus 7x, and then we have what, x to the 4th. And now as we move over here, we subtract, so we're going to get a minus 5x squared minus 7x divided by x to the 4th. Now, notice we have an additional copy of x here. So let's go ahead and factor that. And we've got a negative too. So negative x, 5x plus 7. And I'll write this as x times x cubed. So the x is absorbed. And now we can divide. Of course, we've got a negative on the outside. So we have y prime equals the negative. And so we have what? 5x plus 7. Of course, the negative out here. And then we have the y x cubed. So that's a form of the first derivative. Again, using an alternate form here. Again, not overly difficult, but certainly doable. Now, the thing that we notice about this is that we can apply the quotient rule again, but now we've got the y prime here, but we only have the one occurrence of it. So that kind of, maybe it makes it just a little simpler. I don't know. You may think that when it comes to doing these, you just have to be very careful with the signs and very careful with the arithmetic. Now, for the y prime or y double prime, we'll just apply the quotient rule again. But notice, again, this is set up just like the original. The only difference here is that we held off on dividing from the left-hand side until we cleaned up the right-hand side, getting rid of the additional factors and all. You really do simplify. And again, remember, these are all identities. They are true equations, or valid equations where they are defined. And so that premise allows us to clean up our work because if the derivative exists, it has to be defined there. And so we are okay in cleaning up the work. Now, we can go to the next step. And we'll use this. So I'll go ahead and write this on a clean sheet so we have a little bit more room. So we have y prime equals the negative of 5x plus 7 divided by y x cubed. So we just kind of hold this here. We're going to differentiate this, but that's going to be our substitution. So now we can compute y prime, and it's easy to do. So note y double prime, that is when we differentiate y prime, we just get 2 primes, so that's easy. And now, of course, we can factor the negative here. Just factor it, don't worry about it. We'll just leave it out there until we need to use it. So we differentiate the numerator, we get 5. And then y x cubed, the denominator. So the quotient rule, so I'll just say use quotient rule. Now minus, remember this is factored, don't forget it. We have 5x plus 7. And now we differentiate the denominator. Notice we got a product, so we got y prime, 1 y prime, so y prime x cubed, then plus 3y x squared. So just the derivative of x cubed is 3x squared. We'll just throw the 3 up front, the y we don't change, and the x squared, and we're done with that. So that was, again, remember, what they say, do a little dot there. How'd you do it? Like that. With a little dot, reminding yourself that that is a product. So we have to use the product rule on this piece. And then when we square it, we get y squared x to the sixth. So that gives us a formula that's useful. Now we want to clean it up a little bit, and then we want to make the substitution for y prime. So again, let's do a little bit of algebra. So we've got what? 5 x cubed y. Now we'll just break this up into pieces. So we have minus 5x plus 7. And if you want, yeah, we can go ahead. Let's do this. Let's go ahead and save ourselves having to write an extra line. Let's do this. Let's go ahead and multiply by the x cubed and keep the y prime off to the right. So that'll be 5x to the 4th plus 7x cubed. Again, multiplying by x cubed, y prime right there. Okay? And then, of course, if we want to, you're thinking, you know, we're going to want to absorb the x cubed there, and you probably think just kind of leave it out there, but I went ahead and went backwards, so we'll just live with it. And so now we'll do, what do we have here? We've got minus, and we just want to hit each of these with this, and I'll do this separately. We'll do it in a separate calculation. So we have 3y x squared times 5x plus a 7. So again, 3y x squared times the negative 5x plus 7. Y squared x to the 6th. That is, if you try to neaten something up and you think, well, it's not quite what you wanted, don't worry about it. You've got everything written correctly, and so you're good. So now, if you will, let's go ahead and clean up what we have here. Move all this stuff over. So we have 5x cubed y. And here, if we want to go ahead and multiply this out, this will be what, a minus 15. The 5 times the negative 3, x cubed y. And then, of course, here we've got a negative 21 x squared y. So again, 7 times the negative 3, x squared y right there. Now, this part we can just kind of isolate. Now, again, since I multiplied by the x cubed here, I'm just going to look at this and say, well, we're going to multiply this and just kind of highlight that in the way I'm going to write it. So I'm going to do 5, and I'm going to do x times x cubed plus 7 times x cubed, just making that kind of obvious there. And then I'll bring this down a little bit, just making these brackets a little bit longer. And then here, going ahead and substitute this. Now notice this is negative, and so this will absorb this. I won't absorb that now, but I will eventually. So we have 5x plus 7. I'll do it like this so you can easily see that. And then yx cubed. And then, of course, everything else downstairs, y squared x to the 6th. Now, of course, I can go ahead and absorb the cubes. So they're all gone, okay? Now, notice the negatives here will absorb, so I can go ahead and absorb those, which is easier to do than just putting a plus and then maybe second guessing yourself. So at this point, we have the negative. Now we can combine this. This gives us a negative 10x cubed y minus. Now notice we need a common denominator of y so we can bring this downstairs. So let's go ahead and hit all these with an additional copy of y. So that'll be a y squared. And then, of course, here minus 21x squared y squared. Then we're good to go. the negatives absorbed. And so now we've got what, 5x, so that's a 25. So 5x, 25x squared. And then, let's see, what else do we have? We've got the 7. Oh, well, look how simple that is. Don't do that. I'll expand it later. That's just a 5x plus 7 times a 5x plus 7. We'll expand that later. Just leave that like that. We'll expand it later. And now, again, let me explain what I did. We just have a 5x plus 7 times a 5x plus 7. The negatives absorb. The y, we're going to bring downstairs to join this. But to get the common denominator in the numerator, we've got to hit these with another y. So that's going to give us a negative 10x cubed y squared, and then a negative 21x squared y squared. And then now downstairs, we have y cubed x to the 6th. So again, this just collapses, joins this, but we have to modify these so that we can bring the y downstairs. So we're almost done, and we'll throw the minus in at last, at the very end. So we've got minus 10x cubed y squared minus 21x squared y squared. And go ahead and expand this. So we have plus 25x squared, and 5 times 7 is 35, so that's a 70. So we have plus a 70x, and then what, plus a 49. And then divided by y cubed x to the 6th. Now for the very last one, we'll just throw the negative 3. So this will give us negative negative. So we have 10x cubed y squared plus 21x squared y squared minus 25x squared minus 70x minus a 49 divided by x to the 6th, y to the 3rd, which is y double prime. Now the reason I wanted to do this, and I wrote it kind of large so you could see it, is that if you had worked this with the other technique, as we had in the notes, you get a formula that looks a little simpler. I mean, it does look simpler. For instance, if you compare it, you get this, but the algebra is more difficult. So you get this. Again, we could work it backwards and show that they're equivalent, but this algebra is hard. And so I thought, well, that's fine, but what's nice about this is that it's just really simple. We only had one substitution to do. So when you think about the process, and this is all algebra, this is not, I mean, you're just going to get better at collecting terms, but understanding what the technique is all about. So when you have your y prime, you can compute the y double prime, which basically is, once you apply the quotient rule, as we've done here, that's the derivative at this point. It's the quotient rule. That's the derivative. But cleaning it up, isolating the y prime, substituting for y prime here, so that the result is a formula in x and y only. So again, the technique can be somewhat cumbersome. And you might think, well, in general, maybe all I need is a y prime, but to compute the y double prime, we apply the same technique with explicit functions, but then of course we make the substitution for the y prime, so the result is a function in x and y alone. So as you work these problems, just realize the fact that all of the techniques that you have learned are present to you. All the techniques are available to you. You don't have to invent any new theory. You just establish what the independent variable is, what the dependent variable is, and apply the chain rule to that dependent variable when you differentiate it. In all these cases, Y was the dependent variable. It was a differentiable function of the independent variable X. Now, of course, as you move on in calculus, there'll be more independent variables. And in the calculus 3, you'll see that, and this technique will be extremely valuable, and it will come up many times. So just remember, we are adding a new technique to the differentiation process that does not require that we have an explicit equation. And that is really the power of the derivative. We haven't really noticed that. I mean, you think about equations that are implicit when you study conic sections, the circle, the ellipse, the hyperbola, things like that, the parabola, that can many times be written in a implicit form. So this should not be a surprise to you as far as the implicit equation and its existence, but the differentiation process can be applied in a way that we, again, note we have a very, very usable formula for the second derivative, and we don't have a formula for y itself. We in this particular case could have solved, but you look at some of your homework and see where the explicit calculation of y would not be possible, but that does not keep you away from computing derivatives. And so now, of course, we would just see that this derivative would make good sense away from 0x and 0y. Stay away from the origin. This particular function makes sense. So it's a very, very powerful technique. So enjoy working with the implicit technique. Again, just remember, all you have to do is be a court reporter, as they say. Work with the algebra. Keep everything orderly. Okay, that's all you need to do. You know, as you work things, box things so you can see what is absorbing. Keep track of signs. That way, it'll be very, very efficient. And again, in the next section, we will actually talk about related rates. That is, we'll have formulas that may be connecting variables that are all functions of time, like a radius, a volume, that are connected. And then we apply the implicit technique to get how all of the rates are related. That's why we have the phrase related rates. Because when you apply the implicit technique, you have primes with all the variables, because everything's a differentiable function of t. So we will find how powerful that technique is. And then what we can do is, for instance, solve for a particular rate based upon the given information. And that, as you can very well know, would be quite a great technique that you would find in physics and engineering. So we will continue the process of implicit in the next section. And then, of course, as we move through the calculus sequence, we will find other areas where we can apply the implicit technique. Okay? Well, that's all for now. We'll see you next time for related rates. Thank you.